Hello. So in this video, I'm planning to just talk about the problems related to differentiation and its applications, including mean value theorem, L'Hopital's rule, and Taylor theorem. And then there are some other small corollary after the mean value theorems. So it is not going to be a video that explaining some theorem and then work on the proof, but more likely we're gonna work on exercises. So I think there are like 16 in total. Some of them are short, some of them are long. I will explain the problem first before I do them because I did them like quite a while ago. And then I will start explaining the solutions. And maybe I saw some mistakes. Maybe I need to add more detail in my proof. And also just be aware that since I did this a while ago, I might need more time to think about how to do it. So I will pause the video and resume the video when I get idea back, just to make sure that what I'm gonna say is correct. So it might be feel weird that I froze suddenly and I kind of like going back with a different. Okay, so let's look at the problem one. I'm going to use a different color. Let's use the pink one. Okay, so the first couple of problem is done right after we introduce the definitions, the operations, and I think we use also a little bit mean value theorem. There's no none of them will use none of them need to use L'Hopital's rule or Taylor theorem. We'll see that in the homework set too. So let's look at problem one. It asks us to prove that every Lipschitz continuous function f is also uniformly continuous on A. So when you look at this problem, you need to first think about what is the definition for Lipschitz continuous function and what is definition for uniformly continuous function. Of course, you need to know what is definition for continuity, right? So there are actually two parts. The first one is about the Lipschitz continuous, and the second one is about Hölder's continuous. Let's just focus on the first part right now. So we assume a function that is Lipschitz, and we want to. Oh, so before I explaining everything, I encourage you to pause the video and try to do the problem by yourself. Give yourself like 15 or 20 minutes at least, and then I'm sure you will have some idea, even though you did not solve it completely. And that some idea is really, really helpful for your own understanding of the material. Okay, so let's assume the function f is Lipschitz continuous. And then you might think, what is the definition for Lipschitz continuous? Well, a function with a domain A and map to R is Lipschitz if and only if there is a Lipschitz constant, and we can denote the Lipschitz constant as L, such that the absolute value of fx minus fy is smaller or equal than the Lipschitz constant L times the absolute difference between x and y. So here they are absolute value because we are working on a function that is real valued. If your function, for example, is not from A to R, but from A to Rn, then here should be the Euclidean Rn norm, the here. So just be aware. Okay, so that is our assumption, and we need to use that to prove that f is continuous, right? And then how do you prove f is continuous? Well, there are a couple ways, and we learned that. I think it is in baby rooting chapter 4. So there are a couple ways. The first method, which is we should directly come into our mind, is using the definitions, right? By definition, I mean the delta epsilon delta definition. So let's fix. Okay, so there are some other, you might, like while you're solving the problem, you're not sure which one to use to prove the continuity, right? So the first one's definition and the sequence. The second one, you could use the sequences, right? Like a function is continuous at A if and only for every sequence xn converges to A, fxn also converges to fa. And then there are some others. I will stop thinking for now because we already have our assumptions in terms of epsilon and delta. So I will think pretty naturally that to show the continuity, it's better to use the definition, the epsilon delta definition. So let's fix epsilon. Let's fix epsilon. And we need to find that delta, right? So let's fix epsilon and write down our goal. Okay, so our goal is to show this is smaller than epsilon, right? Given epsilon, we want to show there is this delta such that this quantity is smaller than epsilon. This is our goal. And what we know about assumption is we know this quantity is actually smaller equals than L, which is the Lipschitz constant times absolute distance between X and Y. And therefore, this gives you a hint, right? If we set delta to be, so you want L, so eventually you want L times delta is smaller equals than epsilon, right? So this gives you a hint that delta should be smaller equal than epsilon over L. Therefore, set delta is equal to epsilon over L. And that's why earlier I took delta equals to epsilon over L. So we're done. And then for the second part, let's assume the function f is Holder's continuous. I didn't know Holder's continuous. What does Holder continuous mean before I do this problem? So I Googled it. So you might not know as well. Let me just explain it. So f is Holder continuous if and only if. So I want to clarify that when we say a function that is continuous, we first mean it is continuous at a point. And if we mean that for every point f is continuous, then for every point in this interval f is continuous, then that means that f is continuous on this interval. When we say f is Lipschitz continuous, we're not saying it is Lipschitz continuous at one point. Similarly, when we say f is Holder's continuous, it doesn't make sense to talk about a function's Holder's continuous at a specific point. It's more like a like a behavior that you need to see at least on an interval. So therefore, Holder's continuity definition, there exists alpha such that fx minus fy is smaller equal than m, which you can call this as the first parameter of Holder's continuous continuity, and then is smaller equal than m times x minus y to the power of alpha, and you can call this the second parameter of the Holder continuity. For all x in A, and then alpha is a number between 0 and 1, included 0 and 1. So we suppose we have this, right? And we want to show that f is uniform continuous. Okay. And you need to think about what is the definition for uniform continuity, right? Oh, by the way, I forgot to mention that earlier when we show, so earlier we also need to show uniform continuous. And the reason that this is uniform continuous because the delta does not depend on x. Sorry, I think I forgot to mention that. So while we were proving that delta, if we take delta is equal to epsilon over L, this expression becomes smaller than some quantity smaller than smaller equal than delta. So notice that this still does not equal to x. So therefore, the continuity we're proving here is actually uniform continuity. Okay, let's go back to the second case. If f is Holder's continuous, so again, fixed epsilon, and we want to find a delta such that this quantity is smaller or equal than epsilon, while making sure that delta does not equal to x, right? So if we write fx minus fy, and then we already know that this is smaller or equal than m x minus y to the power of alpha, and then we want to show this is smaller than epsilon, right? So what you do is you set this equal to delta. So you have m delta to the power of alpha is smaller or equal than epsilon. Therefore, take delta is smaller or equal than epsilon over m to the power of 1 over alpha. Therefore, you're done. So therefore, you achieve the uniform continuity. Notice that this does not has an expression x in it. This expression does not have x in it. So it is uniform continuity that we're proving. Okay, so at this point, I finished explaining the first problem. And so I'm trying a new study method, which is after I done a problem and then I learn something from the problem, I will put that into an Anki card. So what I'm going to do now is I'm going to pause the video and I will input the definition of Holder continuity because that is new to me. I didn't know that. I will input the definition of Holder's continuity in that, as well as this problem. So next time when I review my Anki card, I will actually like retrieve, okay, what is the solution? What definitions do I need? What is the method? And I think since it's a simple problem, it should take me a short time to get my memories back. So I will pause the video and I will see you later. Okay, I'm coming back. So let's start with the second problem. Suppose that f is a function from R to R, and there exists some alpha larger than 1, so that we have this inequality. Notice that if you remember the definition for Holder's continuity from problem 1, you should notice that here f is Holder's continuous with parameter that m is equal to 1 and alpha is with the parameter alpha. So for all x, y in R, and notice that the definition for Holder's continuity, that the definition in Holder's continuity mentioned that alpha should be a number that between 0 and 1. It can be 0 or 1. But you might think while you were reading the definition from Wikipedia that why doesn't alpha cannot be can be something larger than 1. And this problem actually shows you it doesn't make sense to define alpha that is strictly larger than 1. Okay, so let's focus on the goal of this problem. So if f is a Holder's continuous function with alpha, the parameter is strictly larger than 1, then show fx equal to f0 for all x in R. So when I was first solving this problem, I was really focusing on showing this equality. In particular, I focus on the point x is equal to 0 a lot, but actually it turns out as long as we show that f is a constant function, then we're basically done, because that immediately implies for every 2 points on the real line, the evaluation of f at those 2 points are equal. So in particular, if you pick x is 0, then they are going to be 0, right? So the difference is going to be 0. So let's just focus on try focus on showing that f is a constant function. Okay, so what is the definition for f to be a constant? Well, for every different elements in R, let's say x and y, fx is equal to fy, right? Okay, and then what do we have is we have a Holder's continuity function. I think this one actually used a little bit, let's see. So I think the hint here is, so the problem here is alpha is larger than 1, right? So that is something making this problem a little bit interesting. So when we look at this, and then we want to figure out what kind of problem it will cause. So let's do alpha is equal to 1 plus beta, where beta is strictly larger than 0 because alpha is strictly larger than 1. So beta is strictly larger than 0. And this actually turns out to be a very important information. So if we rewrite it as this, then we can actually put, so this is equal to, on the right hand side is equal to the absolute value of x minus 1 times the absolute value x times 1 to the power beta. And then we can move that x minus 1 to the left. So therefore, we have this. Notice that this is 1, right? And this is beta. So we have this. And we want to show that this is equal to 0. We want to show the function f is constant, right? So we know this is larger than 0. And what else do we have is we know that the limit, if when x converges to y, this becomes the derivative of y. So we already have this inequality, and then we just put the limit on both sides. So as limit, so the limit as x converges to y, the limit as x converges to y. So here, of course, we obtain 0 because as x converges to y, this becomes to 0. And then what we have? We have the limit is larger or equal than 0, smaller or equal than 0. By the sandwich rule, we have this is equal to 0. And what does that mean by saying that is equal to 0? Well, you recall the definition for derivative, right? So that is just the definition for f prime of y. Therefore, at point y, the derivative of f is equal to 0. And because y is arbitrary, right? We pick x and y arbitrarily from the real line. So y is arbitrary, of course. Therefore, for every y in R, f prime y is equal to 0. Therefore, f is constant everywhere. So in particular, fx is equal to fy for every x. Notice that here x and y are the dummy variables. So I could say fy is equal to f0 for every y in R. And that is our problem. I think what I learned from this problem is it didn't use a lot of definitions, but I think, yeah, the main thing it uses the definition for the derivative, and it uses definition, use the sandwich rule. So, and also you need to be, you need to make the observation that alpha is equal to 1 plus beta, where beta is strictly larger than 0, so that you can divide them, right? So now I'm going to pause the video and put this problem in my Anki card. Okay, let's look at the third problem. I spent some time on this problem because I think there's a trick that you need to, there is an observation that you need to make in order to keep going. And I remember that observation because that took me a long time. So let's look at the problem. The problem is saying that, again, f is a real valued function and defined on the closed interval 0 and 1, and it is twice differentiable. Let me change the color. So twice differentiable means this is differentiable, right? This exists, defined for every x in the closed interval 0 and 1. And what else is we have this is large or equal than 0. And we have this. And so f is monotonic. So here again, let's recall the definition for monotone. F is monotone without loss of generality. Let's just say f is monotonically increasing. So that means for every x smaller than x1 smaller than x2, fx1 is smaller than fx2. Okay, and what do we know about? So we want to show that, right? We want to show that f is a monotone. Another thing that we can try to do is okay, let's forget about it. Let's start working on this problem. So f is defined in this way, and when I was first doing this problem, I was really stuck on the assumption how to use and where to use f times f double prime is larger or equal than 0. So let's notice the observation that f squared, the second derivative of f squared is equal to this expression. And notice that here, exactly same as the expression that given in the condition. So we know this is larger or equal than 0. And we know this is squared, right? So this must be larger or equal than 0. Therefore, we have the second derivative of f square of x is larger or equal than 0. So after we do that, I want to mention that this is larger or equal than 0, and the derivative, the first derivative of this function is larger or equal than 0. Oh, I think I made a typo. So, oh, I did make a typo. Sorry about that. So what I was thinking here is, since the second derivative of f squared of x is larger or equal than 0, that means the first derivative of f squared x must be increasing function, right? So that means f squared derivative is an increasing function on this interval. And eventually we want to show that f is monotonic. Okay, so this is just telling you that the first derivative of f squared of x is monotonically increasing. But that does not tell you that f is monotonically increasing. Recall we have another assumption, which is f0 is equal to 0. If f0 is equal to 0, let me think about this. If f0 is equal to 0, it is not necessarily that f prime of 0 is equal to 0. So let me pause the video and then I'll get back to you. Sorry about that. So I'm back. I think I didn't say anything wrong, but I kind of like interpret my notes incorrectly, and I apologize for that. So the observation we made here is correct. So the second derivative of f squared of x is non-negative because of this expression, and this is square, right? And another observation that we need to make is because we're given that f0 is equal to 0, and f first derivative of fx is equal to 2 fx f prime of x. Sorry, this is not the, this is the fx is equal to this, right? And therefore, the first derivative of f squared evaluated at 0 is equal to 2 times f0 f prime of x. And because f0 is equal to 0, so this is equal to 0. And that's why the first derivative of this function f squared is equal to 0. And because the second derivative of f squared is non-negative, that means f prime, that means the first derivative of f squared is larger or equal than, is increasing function. Okay, it is increasing function. Therefore, for every x that is larger than 0, f prime, like the first derivative of f squared at a point that is larger than 0 is going to be larger than 0. So what I so since the domain of function f is from 0 to 1, which is larger or equal than 0, that means for every point x in 0 and 1, the first derivative of the function f squared evaluated at any point on the closed interval 0 and 1 is going to be larger or equal than 0. And therefore, since we have the first derivative of f squared is non-negative, that implies our original function f squared is monotonic increasing. So but our goal is to show f is monotonic increasing. So far we have derived that f squared is monotonic function. So we need to argue a little bit about that. So what is the relationship between f and f squared? Well, since f is defined only on 0 and 1, we have that f would be in so let me okay, so f squared, so the direct relationship between f and f squared is f is equal to positive negative square root of f squared, right? So if you look at the function positive f square root, since f squared is a monotonic function and square root is monotonic function, this whole thing together is monotonic function. And then because this is a monotonic function, the negative version of this function is also monotonic, but decreasing. So we are almost done. You need to argue a little bit that since fx is equal to positive negative square root of f squared x, you need to argue a little bit that it is impossible to have f is equal to positive square on the domain on some part of the domain, and then it is equal to negative square on some part of the domain. And I think that one, I need to pause the video to think more because I think what I wrote here is not complete. Okay, so let me start explaining. So we're good at explaining that the second derivative of f squared is non-negative. Therefore, the first derivative of square is increasing, and because the first derivative of function f squared evaluated at 0 is equal to 0, so for any point onwards, which means the whole domain of f, which is closing with 0, 1, the function is going, the first derivative of f squared evaluated for any point larger than 0 is going to be larger than 0. And because the first derivative of a function is non-negative, right? That implies that the function itself, which is the function f squared, is going to be increasing, which is monotonic increasing. And therefore, what we have is, therefore we have that f squared is monotonically increasing monotonic function. What else we need to argue is we need to explore the relationship between f and f squared. So of course, f is equal to positive negative square root of f squared. If you look at the function square root of f squared, that is, since f squared is monotonic function, and the square root of a function is also is also a monotonic function. Therefore, the composition is still a monotonic function. And on the other hand, because the negative part of the negative of a monotonic function is still monotonic. So no matter f is equal to positive square root of f squared or f is equal to negative square root of f squared, f is going to be monotonic. The only thing that we need to take care is we need to argue that it is impossible for f to take value negative square root x squared at some point in the domain, while it is equal to positive f squared, positive square root of f squared at some point in the domain. That is not gonna happen, and we need to argue that a little bit. So the arguments here, let me write down like from scratch. So we have f is equal to, so let's prove by contradiction, right? Let's suppose there is x1, x2 such that fx1 is equal to positive f squared x1, and fx2 is equal to negative f squared x1. Then that implies what? The f squared fx1 times fx2 is equal to it's not equal to, but it's going to be strictly smaller than 0, right? So because it's strictly smaller than 0, that implies for example, x1 is smaller than 0 and fx2 is larger than 0. So that implies, so if you look at the function at x1, it is less than 0, at x2 is positive, which is larger than 0. So something like look like this. So that implies there exists C between x1, x2. Also, we need to specify that x1, x2 is actually selected from the domain of f, which is close interval 0, 1. There exists C in x1, x2 such that f C is equal to 0. And this holds by intermediate value theorem because f is differentiable. Yeah, it is twice differentiable. Of course, it's differentiable. So f is continuous. Okay, so by intermediate value theorem, we have that. And then once we have that, we should reach a contradiction. Why? So, but 0 margin x1 smaller than xc, smaller than x2. Okay, and f0 is equal to 0. F is monotonically the monotonic function, which means f could c should be either strictly larger than 0 or smaller larger than 0, but it is so contradiction. It cannot be equal to 0. Okay, therefore we're done with this problem. And let me pause the video and put into my entry card. Okay, so let's look at another problem. This is a problem 2 from chapter 5 ruling textbook. It has 2 parts. The first part is as so if we're given that the first derivative of f is strictly larger than 0, then we want to show that f is strictly increasing. Well, the first thing came into my mind is to use the mean-value theorem because if f is continuous on the closed interval AB and differentiable on open interval AB, that implies fb minus fa is equal to f prime. So there exists the x between a and b such that the fb minus a is equal to f prime of x times b minus a. So because we have information about f prime, we have information about and we want to show information about the monotonicity of function f, which involves with difference of x versus difference of fx, right? So that's all the elements. That's all the elements covered in mean-value theorem. That's perfect. So if you write down the mean-value theorem as I did right here, you can see that because this is suppose x2 is larger than x1, and then we also know that by condition at the beginning that this is strictly larger than 0, therefore this is a strictly larger than 0, and hence whenever the derivative is strictly larger than 0, f is strictly monotonic increasing, and that's the easy part. And the second one is that GB is inverse function. So what is the inverse function? Well, it just simply f inverse. So if that is written as f to the power of -1. And we want to show that f is differentiable and the derivative is exactly in this formula. Okay, so the second part is to show G is differentiable. We know f is differentiable, and then we know there's a special relationship between x and y. So I would try to use definition to show that G is differentiable first. So the definition for G is differentiable is the limit exists, right? The limit exists. Which means that so I actually wrote down here, the limit of g of ft minus g of fx divided by ft minus fx exists if and only if g is differentiable. Notice that here I fit in the value ft, fx, ft, fx, because g is inverse of f. So if you think f is a function from f is a function from a b. Sorry, AB to R, then G should be a function from F AB. So the domain of G is actually F AB. Okay, so we want to show the existence of the limit, and we're gonna take advantage of the hypothesis that F is differentiable, right? So this is equal to this using the definition for inverse function. And as you notice that rearrange it a little bit, we obtain this. So not only okay, so because we have this and we know F is differentiable, so we know this is defined. Therefore, the limit defined, therefore F is differentiable. And in particular, so we can like prove the two things together. We also prove that the G prime is equal to 1 over F prime X. Okay, so that is this problem. I think this problem is relatively easy. You just need to so keep in mind about the mean value theorem and the definitions of derivative. Okay, let's look at the next problem. Is problem 3 in chapter 5 in rooting. So the problem is like this. So G is a real value function on R, and its derivative is bounded about by the absolute value of G is bounded by M. And we also have a function F, and we want to show that F is 1 to 1 given that epsilon is small enough. So basically we want to show that there exists an epsilon such that for like every value that is smaller than that epsilon, F is 1 to 1. So as long as you can make the choice of like the cutoff of epsilon small enough that so that F is going to be a 1 to 1 function. And so when you look at this problem, you first wonder what is the definition for 1 to 1, right? Well, the definition for 1 to 1 is you have one value on X axis and that corresponding to one value on the Y axis. You can prove this, but F is 1 to 1 if and only if F is monotonic. Strictly monotonic. So we want to show, and F is strictly monotonic if and only if the first derivative of F is strictly larger than 0. And I think we proved earlier if F is strictly increasing. So F is 1 to 1 if and only F is strictly increasing or strictly decreasing. Okay. And here F is okay, so our goal is to show that the F prime of X is strictly larger than 0, given that given that the epsilon is small enough. So we already have. So let's calculate the F derivative first, right? The F derivative is equal to 1 plus epsilon times G prime of X, and because 1 is larger than 0, we just need to make sure that epsilon times G prime of X is equal to be smaller than 1. And we want to make sure this happens. Okay. Well, if we show that the epsilon, let me think, is smaller than 1, then since G prime of X is smaller than M, or negative G prime is smaller than M, epsilon times G prime of X is equal than epsilon times M, which is smaller equal than 1. want to show. This is want to show. Therefore, we should choose epsilon to be smaller or equal than 1 over m. And then we're done. And I'll be back. Okay, now let's look at the next problem. So we have, we're given that this, sorry about that. We're given that this one holds, and we also given that, so those are real constant, and then we want to prove the equation has at least one real root between 0 and 1. Okay, and how do we prove that? If we want to prove that fx is equal to 0, has a solution, at least one solution between 0 and 1, what do we want to use? Well, I have a very, I don't remember, but I feel like I used Taylor theorem there, and I try to recall why do I need to, what is the intuition for using Taylor theorem? Okay, so I think I recall. So when you first look at this problem, like you mean like me that I have no clue where to go, because I feel like this is asking to solve a polynomial problem. But actually the hints is everywhere in the problem. So for example, this between 0 and 1 is a hint. So I will label that as a hint. So that actually it actually leads us to think about the interval, the closed interval 0 and 1. And at least one root, this is another hint. So this is actually letting us to show the existence, quantify existence. So we want to show there exists x in 0 and 1, combining 1 and 2. Okay, and there are more hints. Okay, so what is the, okay, so so you might wonder, what does this do? What's the relationship between this one, and this one? Well, they're very similar, except, yeah, they're very similar, but you need you need to do some work to see the relationship. So this is f, and because we just learn the differentiation, so when you look at a function, you want to do differentiation, and that's how the intuition comes into my mind. So if we have function fx, that is, and then we have if we do the derivative, right? So this is equal to, the first one is equal to 0, and the second one is c1, and then so c1 and then 2 times c2 and x1. Let me think about. Actually, what I think I shouldn't do derivative. Let me erase it. So you are trying, right? Like once you have a problem, you'll try everything out. So I actually think. So I'm trying to find the relationship between these two. And I observe that the integral of this function so is equal to f0 x plus c1 x squared over 2 plus, so this is c2 x squared, c2 over 3 times x 3 right, and then plus dot 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 plus cn over n plus 1 times xn. So, and then I see the relationship between this and this more directly, because if I define this function to be fx, and this is just f evaluated at 0, evaluated with 1, right? Okay. And we also know that f evaluated at 0 is equal to what? It's equal to 0. So if we want to use, if we try the mean value theorem, so then maybe with f1 minus f0 is equal to, like, why do I want to use the mean value theorem? Because our goal is to show the existence of an element in certain interval has certain properties. So that just reminds me of the mean value theorem. So f1 minus f0 is equal to, so by mean value theorem, there exists x in 0 and 1 such that this satisfies f prime of x is equal to 1 minus 0. And then what is it? This is equal to c1 plus c2 over 2 plus da 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 plus cn over n plus 1. And f0 is equal to 0, right? So this is, and then this is equal to the derivative of I prime, right? Well, the derivative is really, sorry, this one should be, I wrote it down. F1 is equal to 0, 1, right? And then the derivative, so this is equal to C0 plus C1x plus beta plus Cnxn, right? Times 1. So actually I think I made a mistake because f0 of this function is equal to 0. F1 of this function is equal to this. Oh, right, because this is equal to 0. See, we're using this assumption now. Right, so this is equal to 0, 4. Therefore, there exists x in the interval 0, 1 such that c0 plus c1 x plus cnxn is equal to 0. And therefore, we're done. Okay. Okay, let's go to look at the next problem. So we have a function f that defines the differentiable for every x larger than 0, and we are given that the derivative of f at every x is actually, sorry, we're given that the f prime of x converges to 0 as x converges to infinity. So here, I think the domain of f is, if it's not specified, it's just a real line. And then we define gx is equal to this, and then we want to show that gx converges to 0 as x converges to infinity. So again, I think the trick is to find how to apply mean value theorem. So I feel like, honestly, like without knowing that we're learning mean value theorem, I wouldn't thought about using that because, well, to be fair, like the problem does involve the derivative, right? It does involve its derivative of function f, and if you look at the expression here, it is a difference between the function f evaluated at 2 points. So maybe that's the direction to talk about using the mean value theorem. So, and then moreover, even though the mean value theorem applies on constant interval a and b, you can actually use it more flexibly. So for example, here we're actually apply the mu-maximum on x plus 1, right? And you can check the condition. So by mu-minus theorem, it is equal to fx plus 1 minus fx is equal to, so there exists a c in x plus 1 such that this equality equals f prime c x plus 1 minus 1. So this is equal to 0. So we have, and then because if you take the limit on both sides, so which x converges to infinity, plus 1, x converges to infinity, f prime of c, right? So here, the c is actually tightly linked to x because c is the value between x and x plus 1. So as f converges to infinity, c also converges to infinity. Therefore, this is equivalent as the limit of c converges to infinity f c. And then this is equal to 0 as we stated here. And therefore, we have the limit. This is equal to the limit as x converges to infinity of gx. Therefore, we're done. Okay, let's look at the next problem. So f is, so we have some information about function f. We know that f is continuous for every x larger than 0, and we also know that f is differentiable. And then we also know that f0 is equal to 0, f prime is monotonically increasing, right? Which gives us that f double prime is equal, is not straight, is larger or equal than 0 if f double prime exists, but we may not need to use that here. Okay, and then we define that gx is equal to fx divided by x, and then we want to show that g is monotonically increasing. Again, g is monotonically increasing if and only if g prime of x is larger or equal than 0 for every x. So our goal is actually relate to the first derivative of function g, and that leads us to compute the first derivative of g. So I compute it here. G prime is equal to this expression, and let's digest each expression individually. So we know this is larger or equal than 0, right? Okay, and oh, actually, so let me rewrite everything. So g prime of x is equal to x times f prime of x minus fx times 1 divided by x squared, and that is equal to f prime of x minus fx divided by x divided by x. Okay. How will that help us? Let me pause the video. Okay, I'm back. Let's work on number 6. I think I already stated the problem, so let's work on it. So I was on the right track. So gx is equal to fx divided by x, and g prime of x is equal to x times f prime of x minus fx times 1 divided by x squared, which is equal to f prime of x minus fx minus x divided by x, right? So we divide x on both sides. And then what is a good observation is we're going to use mean-value theorem. So if you look at this part, fx divided by x is equal to fx minus f0 divided by x minus 0, right? And then we, since, okay, let's just check the conditions together. F is continuous, 0, infinity, f is differentiable on 0, infinity. So by mean value theorem implies that there exists. And I think in particular, it is correct on 0x. 0x. So by mean value theorem, there exists a c in the open interval 0x such that fx minus f0 is equal to f prime of c times x minus 0. And then how will that help us? We can replace this with f prime of x minus f prime of c divided by x. Recall or notice f prime is monotonically increasing. So since because c is in 0x, so because c is smaller or equal than x, right? Therefore, f prime of x minus f prime of c is larger than 0. And x is larger than 0. Therefore, this whole expression is going to be large or equal than 0. Therefore, g prime of x is non-negative, so g is monotonically increasing, and we're done with this proof. I think the key idea is still using the mean value theorem. You need to recognize which is the which place you need to apply mean value theorem, and there are some hints that you need to be careful when you're reading the problem statement. Like for example, you need to translate this problem into this form, and you can see, and you also need to realize that there is a reason the author gave us f0 is equal to 0, this condition, so we can translate this specific expression into this specific expression. And once you arrive here, you should realize the need to use mean value theorem. Okay. Okay, now let's look at a different problem. So let's read the problem together. F is continuous. F prime is also continuous. On the closed interval 0, 1, notice that it is also a compact interval. And we are showing this for x, y in 0, 1. So the proof is pretty simple. If you recall a corollary after the mean value theorem, so fx minus fy is smaller or equal than supremum t in 0, 1 f prime of t times x minus 1. So this is a corollary after mean value theorem. And because f prime is continuous on the compact interval, it assumes maximum. Therefore, it is equal to this. And then we're done. Okay, let's look at the next problem. This one is a little bit more involved. I spent quite a long time to figure this one out. So I'm going to explain along with my notes, and I will add some detail when needed. Okay. So let's look at the problem itself. Again, f is continuous and f prime is also continuous. At this point, you might detect a pattern that whenever you have something continuous on compact interval, you may need to use a uniform continuity. Okay, and we define M to be a set of a critical point actually. So M is actually a set of points like this. Let me try a new thing. Cool. Okay, so let me see if I can change the. No, I cannot change the size of the pen. Okay, seems like not. So what I'm going to show is, so M is defined in this way, right? So the peak point where the derivative is equal to 0. And the statement is very easy. Like after including those simple conditions, we want to show that M cannot contain an interval. What does it mean by interval? Which means interval is a set point that is uncountably many when we're talking about interval or real line. Okay. And then show by example, which is easy. You can think about it. You can think about this particular example. You can draw it on decimal. That indeed has infinitely many points in M. Okay, so our main goal is to show the statement that M cannot contain an interval. So when you firstly get this statement, it may be really hard to start, like you don't know where to start with. So something like this like contains an interval. It is better to start with contradiction. I would say like sometimes whenever I feel like a statement is not very clear, for example, the goal of the statement cannot be expressed in terms of a definition or in terms of mathematical, at least so far as I know, I don't know how to express that as a mathematical rigorous expression. I usually will go with contradiction. So let's assume M does contain an interval. And what does it mean by interval? So if you have countably many points in that set, then it is not an interval. Interval or real line means uncountably many points, and not just uncountably many. For example, rational numbers are uncountably many, right? But it is still not an interval. We need continuous uncountably many. So my point is there are many points in M, and those points form an interval in M. So suppose that F contains an interval. This means that there are not just uncountable many. This word is inaccurate. There are many points. Right. In point M, and so here I basically interpreted a little bit about the definition of function, because the function it could be 1-to-1 or it could be more to one, but it cannot be 1-to-more because that's just not the definition for function. Therefore, if you have many points in the set M, well, you can think about 1-to-1. So there are many points on the corresponding x, right? There's interval in the real line such that each point corresponding to one point in the interval contained in M. If your function is more to one, then M contains an interval implies that the pre-image of that interval contains more points as well. So the overall conclusion of this paragraph, and then because the function f is continuous, so we can use an intermediate value theorem to show the existence of such x such that fx is corresponding to one element in M. So the conclusion of this whole paragraph is just, I want to show, like, suppose that we have an interval in M. I'm saying that there must be many points in the corresponding x-axis. Okay. Moreover, we know that f prime is continuous, right? Because f prime is continuous on compact, it's a uniform continuous. And again, the uniform continuity, you can think about epsilon delta definition, and the delta does not depend on x. So for every x and y, right? So given epsilon, here epsilon could be 1/n, and for n in natural number. So that's why I have for every n there exists delta, which does not equal to that, which does not depend on x, such that this implication holds smaller than 1 over n. Okay, and now let's fix n. Let's fix n. So this is what? This is the distance between any point, the distance of the distance between any 2 points, f1, f2, fx1, fx2, where x1, x2 can be any point on the domain. So in particular, if we so recall we have I in M, right? And then we're defining C. So those are on y-axis. And now define C to be on x-axis, where each element in the C corresponding to each element in this interval. So mathematically, we can write an element is in C if this element satisfy the property that the first derivative of f evaluated at this point is equal to 0. Otherwise, in other words, you can say this contains elements such that the function evaluated at this point is actually contained in M. Okay, so geometrically, so if this is a function of f, right, and then we have some critical points, and each of the points is in M, and then the corresponding the pre-image, we can call it pre-image. So corresponding element on the x-axis are those, and then we said those points are belong to set C. We denote the set, they form a set, and then we denote that set as the capitalized C. Okay, so recall that we are actually given a hint, and the hint is saying that because the hint tells us to utilize the condition that f prime is uniformly continuous, and think about the image under f of a small ball around a critical point. So let's do that. So let's pick a critical point. Like for example, let's pick a critical point here, right? And we're looking at the image of the image. And so this is a critical point, and this is corresponding point on the x-axis, and this is the little ball around that x element. And we're looking at the image of this ball. So let's look at the image of this ball. I draw a line. So on the super far left of this, I notice that because this is just R, so this is actually not a ball, but an open interval. So on the super left here, it's corresponding to this value. On the super right here, it's corresponding to this value. And the image, the cover is actually from this value to this value, right? Because when we evaluate here, when you evaluate here, it is this point equal to this point, so you don't have to double count that. Okay, so what I'm going to say is, because there are so many points in the C, we can actually reduce. We don't need those many points. Actually, we just need the points. We just need the points so that we can form a certain type of cover of the interval I in M, and you will find why we want to do that. So, so the idea is like we have many balls that will prove the statement is wrong, i.e. will reach a contradiction, but actually in our proof, we don't even need that many points, okay? So we only need the points as much as we just need the number of points so that we can prove the statement has a contradiction. And then that's why we can actually reduce to the point and only left the point such that for each xi, xj in C, the distance of them is smaller than delta. So here, if you see this point, their distance is smaller than delta. So we just need this many points. That's enough for us. Okay, so if the distance is delta over the distance delta, and then the whole length is let's see, what is the whole length? The whole length is c. Okay, so this c is different from the ci. This capitalized means the set, right? The set of the points, the set of the center of our cover. This c is the length of the. This is actually the length of the interval I. Okay, so where are we? So the diameter of the ball is epsilon in this way, right? Therefore, how many? We have the length is equal to c, and we need to make sure the diameter of the ball is epsilon. So there is at least c over epsilon many elements that we need to make sure this happens. So what do we have now is that we have really good cover to cover the interval I, which is contained in M. And we're looking at each ball. And then notice that because the way we construct this open cover, each element, the ball is going to be less than delta over 2. Let's see, in the neighborhood of xi. Right. So if let's just focus on this purple ball. Let's focus on this. By the corollary of Taylor theorem, if we pick any 2 points inside of this interval, which is xi minus delta over 2 xi plus delta over 2. So those 2 points, the distance must be less than the diameter delta, right? So let's just write down, let's just apply the corollary of the Taylor theorem on those 2 points on this interval, xi minus delta xi plus delta. So we have this expression. We have this expression. Right, so the supremum here is actually over this little ball. And here the observation, I think this is a pretty critical observation that we need to make to continue, is that because f prime is uniformly continuous, and therefore when we try to recall the epsilon delta, it does not actually depend on where you are. It doesn't depend on which x you're dealing with, right? So that gives us information that this supremum is also the supremum is equal to this minus this because we just subtracted 0, right? So the supremum between, we know at this point, this is x, this corresponding to xi, where xi is this point here, right? So corresponding to this point xi, the first derivative of f is equal to 0. And because the first derivative of f is equal to 0, we know that we know that for any point in this interval, if you compare the difference f prime t minus f prime s, where s is any point on this interval, xi minus delta, xi plus delta, then the difference is going to be smaller than 1 over n. Why? Because again, it goes back to uniform continuity. Because of this one, uniform continuity. So for any 2 point in a ball where each point is less than delta, the evaluation of f on those 2 points, the evaluation of f prime on those 2 points. Sorry, here I forgot prime. The evaluation of f prime on these 2 points can no larger than 1 over n. Therefore, we already know one point is 0, right? And another point in this ball, and you divide the difference of them. Evaluate the difference using f prime function. It must be smaller than 1 over n. Therefore, okay, what do we have now? We have this is smaller than 1 over n times delta. So this at the end we have the we have this is smaller or equal than delta over n. Okay, and then now we're going to show what exactly is the contradiction. So the contradiction here, if we have Fm is smaller or equal than, notice that we form a cover, right? Actually, here is not m, here is I. So I is the interval that we assume is containing m. So here, if you say fi, and then notice that this bar is the cover, bi is the cover of the interval I. So by the property of the union, the function, you should learn that in the previous chapter 2. And then this is smaller than this. And then, oh, I'm sorry. So this is just by definition. So of the open cover. So we read I in terms of this. And because the open cover may be some extra stuff than just I itself, therefore there exists a smaller equal sign. And from here to here, we actually use that function of union smaller than the summation of the function of each set. So you have something like this. And then notice that when we are actually another convention here I'm using is like when you evaluate a function on a set, this is not a set, it is a scalar. It may be confusing. This just means the maximum difference when you evaluate 2 points from this neighborhood. So here, for each ball, no matter which 2 points you select from this ball, the difference is going to be smaller than delta, right? And then the f evaluate on this ball is going to be smaller than delta over n as we proved here. Okay, so do some algebra. At the end, we receive that fi is smaller or equal than c over n. And notice that the c does not depend on n. It's actually like a constant. And if you remember, the c represents the length of the interval I. And then so we have something, we have 0, we have this, it's larger than 0, smaller than this. And as n converges to infinity, this term converges to 0. Therefore, by sandwich rule, I'm going to highlight using yellow or something, hopefully. Yeah, this balloon is equal to 0 as n goes to infinity. But so notice that again, recall the convention. I'm not saying this is a set because I is a set. I'm not saying this is a set. This notation just means the difference between the maximum difference between the 2 points that we evaluate when the 2 points are selected from the interval I. So here we see that this is actually 0 as n goes to infinity. So that means, and notice that where does n come from? This n come from when we introduce epsilon. So because of the uniform continuity for every epsilon, right? And instead of doing for every epsilon, we're doing for every n, and we replace epsilon with 1 over n, which is totally allowed, okay? And that means for every n, right? If this inequality, if this inequality holds, which inequality I'm thinking, if this inequality holds for every n in natural number, then it must mean fi is equal to 0. Well, fi is equal to 0, it just means what is the length for the I, what is the length of, right? It's just 0. So it does not include an interval. Therefore, we reach a contradiction. I hope the proof is clear. If I had any mistake or typo, please let me know. Otherwise, we can move on to the next problem. Okay, the next problem is relatively easy. So we learned about Riemann sum, and this is just use the definition for of lower sum, upper sum, and you take the limit as n goes to infinity. So using the definition of the Riemann sum. Recall what is the definition for Riemann sum, right? It is this one is equal to and you can choose either one to compute. For example, I chose this one. I choose to compute this one, and to sorry, I choose to compute. Sorry, I choose to compute this one, and this one is the supremum as lower sum of function x2. Sorry, supremum over partition. And this is x squared. And this is alpha. Alpha is equal to x, so usually we don't write alpha. Okay, so we have this. And then you compute this, and you take the n goes to infinity. You can pause the video and you can look at my solution to check if it is same as yours. The procedure is pretty standard. I would say at the end there may be a little trick that you don't know is the series I is equal to 1 to n of I squared is equal to this. And that's the only thing you need to know. And then you need to create a partition. So the way that I create the partition is this way. Okay, so let's look at the next problem. It seems okay. So suppose f prime is a continuous on AB, epsilon larger than 0. Prove that there exists a delta larger than 0 such that we have this hold. Okay, I think I remember how to do this problem. Right. Again, it used the uniform continuity because f prime, we're given f prime is continuous and on a compact interval, right? So the trick is here is, and it also used the mean-value theorem. Why? Because you can rewrite this expression. So there exists c, right? So this is equal to c. There exists a c in the interval x comma t. Okay, so f prime c minus f prime of x, the absolute value smaller than epsilon. So we have this. And because we have this, and because we know f is continuous, so we know we have uniform continuity. So we know there exists delta independent on x such that implies this. And therefore we're done. I think we're done. Let me double check before getting back to you. Yes, I think this one holds because our goal is to show this, right? And then by the mean-value theorem, it is equivalent as to show this. And this is true because given that f prime assume maximum, given that f prime is uniformly continuous. Okay. And the next one is suppose f is defined in a neighborhood of x. Suppose f double prime exists, show that the limit of this is equal to that. I think what I am, first of all, the hint using the theorem 5.13 is L'Hopital's rule. Okay, I recall. So we need to use L'Hopital's rule for that. Why we can use that? We'll check the conditions, right? So as h converges to 0, the numerator converges to 0, the denominator converges to 0. So the conditions are satisfied. And using L'Hopital's rule, we need to compute the derivative of both numerator and denominator, right? With respect to h, and I computed that here, and then I continue to simplify it to this, and then I simplified into this, and once I simplified into this, I recall, okay, this is by mean-value theorem, right? So we're applying mean-value theorem here. There exists c between x minus h, comma x plus h, and then we have the limit as h converges to 0. And because c is in this interval, as h converges to 0, c must converges to x. Therefore, we can replace. We can replace this. Yeah, not replace. This is just equal to f double prime of x. Okay, so let's look at number 23. Number 23, let me see how many. Well, I'm sorry, there's so many problems that I missed down. Okay, so I decide to, because of the time constraint, I am going to state some simple ideas rather than going into the detail of the problem. Okay, so for this problem, I would say it is very classical, and I encourage you to work out by your own. There are some tricks that I didn't get through. I have to look at the hint, and you're welcome to use some hint and continue to solve the problem by yourself. So the main idea, so let's just look at the problem, right? Okay, so there's a new concept which is convex, satisfies this inequality, and we want to show that every convex function is continuous. So that is our first statement, and this oh, and also we need to show this. I think I forgot to show this. I will show later, but our main focus is to show that I will give some outline of the proof regarding to this claim, which is every convex function is continuous. And this is actually the hint. So you prove this first, and then you prove that second. So to prove the hint, this intuition really helped me a lot. So if you draw a line on the x-axis, and then you draw f is a convex function, and you connect those dots using the secant line, and you can see that as corresponding to different 2 points in specific order, the secant line has a slope that is increasing. So that is basically the idea of the convex function, and that's what we're trying to show for the first claim. And once you know the trick is pretty simple, I would say, just the algebra stuff. So I would tell you the trick, and then you can work by yourself. Okay, so the trick is because so we have So we have those points, right? We have those points, and notice that the T is the middle point between S and U. So what does that mean? That means you can write T in linear combination of S and U. So for example, I write T in this way, and the corresponding lambda you can rewrite it to find the expression for lambda. And once you do that, you utilize the condition of convex function. F is a convex function. So what you have is you have F is a function, so it satisfies A, and from this inequality, you can actually deduce the inequality. So I'll mark here 3 and 4. So just by this much information, you can actually derive inequality 4 over here. And then you write T in slightly different way. And you utilize the definition of convex function, and you can actually figure out inequality for number 3. And that's it. So as I said, you probably have, like I didn't have any clue at the beginning, but once you know the trick about writing T as a linear combination of the side extremas, which is S and U, and then use the definition for convexity, then you can get a desired inequality just by some algebra. Okay, and once we show that, so I'm going to clear out my notes. So the next thing, the continuity comes later. So as a corollary, so to show that, you also need to show a corollary. So instead of having this 3 point, so I'm going to use so instead of having these 3 points, you are extend the claim to be like 4, so you can have this inequality. And once you have this inequality, you can use this to prove the continuity claim. What is a continuity, right? The continuity is so here you can pause the video and check my work. Basically, what I did is I proved that corollary 2. Okay. So I need to use that for the continuity. And what is definition for continuity? Okay, so the definition for continuity here, we are going to use the epsilon delta definition, and which involves with fy minus fx is smaller than delta, and we need to find epsilon. Sorry, fx minus fy smaller than epsilon, given that we need to not given. We need to find the delta, right? Desired delta to make that work. Right. So if you rewrite, like mark the points on the interval AB, you have x, y, y1, and y2. So what I did is I firstly focus on this half interval, and notice that it's corresponding to T, U, B in our in the corollary that we just proved, and then you can apply the corollary on those 3 points. After you apply the corollary on the 3 points, sorry, on those 4 points, on those 4 points, because the corollary involves these 4 points right here. So you apply the corollary on those 4 points, you get the inequality, and you define this inequality to be C1. And then similarly, what I did is so this is X, this is Y here, are our 2 interest points. And you pick 2 points on the left of X. Like notice before we pick 2 points on the right here and pick 2 points on the left of X. And you apply the corollary again on those 4 points, and you obtain this, and you call it C2. Therefore, notice that this sorry, this is smaller or equal than C1, and it is larger or equal than C2, as I indicated here. And what is C1, C2? Well, C1, C2 is okay, so sorry, so this holds. I think actually I need to So let me try if I'm writing the correct thing. So if it's smaller than C1, then definitely smaller than the maximum C1, C2. If it's larger than C2, then it is larger than the maximum C1. I think that is not correct, right? I think that is not correct because C2 and C1, what if C2 is smaller than C1 and you're larger than C2? I think what I need is I need to change this to min. And okay, what is C1 and C2? C1 and C2 are this. And I think what I can do is those are actually bounded by some number t, like negative t. Therefore, we can have this is equal to smaller equal than t. This is t times y minus x. Therefore, we just need to choose delta to be absolute over t. And then we showed the proved. I think t exists, such t exists because the fact that f prime because C1 and C2 are finite values. So the mean. Oh, I'm sorry. I think I'm sorry. I think this is correct. So max. Let me pause a little bit and think more. Sorry, I think what I said is incorrect. Let's just keep this version because that one is not correct. Okay. The next problem is also a little bit challenging. So I will, again, I don't have time to go over them in detail, but I will state the outline. So the problem is kind of simple and it's very classic calculus rule that f is differentiable. And we want to show that the f is convex if and only if f prime is monotonically increasing. So recall in calculus, we have this, and the corresponding f prime is going to be this. It's very natural, and then you can understand geometrically very easily. So we need to prove that. And to prove this problem, to prove the statement, we actually need to use a corollary that we discussed in the previous problem. I will remind you when we need that. So suppose that f is convex and we want to show that f prime is monotonically increasing. We need to use the corollary from the last problem. So here define we have this, and by the corollary we have this, and which is similar to this, which is switched. So the sign is not changed, right? Okay, and we have limit on both sides. So first time we take the limit as t equals to x1, and this one does not affect, so just itself. And then we obtain on the left, this converges to f prime x1, on the right, it just itself. And then we apply the limit as u converges to x2 on both sides. And then because this converges to f prime x2, and the left just itself. Okay, and then we're done. So this is a very simple application of the previous corollary. Okay, now we want to show that if f prime is increasing, then f is convex, and then we're gonna show that by contradiction. So suppose it is not convex, that means there exists a point in the middle such that the inequality, we call the inequality to define the convexity of a function. There is a reverse inequality. So mathematically, we write there exists a lambda such that there exists there is a lambda such that this inequality holds. So normally, if you recall the definition for convexity, it is smaller or equal than, but here it's large because we want to show a contradiction. Okay, and then we're gonna use the mean value theorem, right? So what we're gonna do is, what we're gonna do is we have x1 and we have x2, and we are going to firstly focus on x1, okay? So we pick a point k here, and we're only focused on this specific interval. And then you can check the condition, but we can apply the mean value theorem here. So if we focus on this interval, there exists the C1. So the reason that I focus on this two is like this is x1, this is x2, and I split them into two using k. And then here I'm gonna have C1, and then here I'm gonna have C2, and therefore you can compare the f prime value evaluated at those 2 points, see if those are aligned with our assumption, right? Or it will derive a contradiction. So let's first focus on this interval, and by the mean value theorem we have this. And now we need to replace, we want to use assumption that it's not convex, right? Because it's specific k. We can write, so here just apply the definition of here. And then at the end of it, we got this one. So we have so we have this inequality. Okay, and then we can write k in terms of this. So before my k is before my k is this, so lambda 0 x1. Now I rewrite my k to be this. There's no particular reason. You can also use a method that I wrote here, which is much simpler. So once you write k differently, and then you apply exactly same method on this k, but on this interval k x2, because I want to split x1, x2 by k, so there is this point, there is this point. So there is this point because C2 satisfies this inequality. And once the C2 satisfies this inequality, we actually together we have this inequality. Let's see. Hence we have this inequality. Let's see. How is that a contradiction? Well, we have this ordered, but we know that f prime is monotonically increasing. And because that is monotonically increasing, that means given C2 larger than C1, f prime of C2 is supposed to be larger or equal than f prime of C1. But we see an opposite here since we reached the contradiction. And that is the proof. And I forgot to mention there's a second part of this proof, which is prove this, but it is very trivial because we using the mean value theorem, we can show that this is large or equal than 0 if and only if f prime is monotonically F prime is monotonic increasing, and which implies the convexity, and vice versa. So we're done with this proof. And then the next proof is, let's read it a little bit. It looks complicated, but I think overall it's okay, not that bad. So A is a real number, and F is twice differentiable real function. And we have those three, which are the upper bounded for this, this, and this. And then we want to show this inequality. And how do you show this inequality? Well, follow the hint. So simply follow the hint. The Taylor theorem, we need to show, first of all, using the Taylor theorem, we show this. And hence, right, we have this. And then we're done. Okay, so let's show using this Taylor theorem. Well, I think I won't show the detail here, but the main method is, I think I found a trick while I was working on a problem related to Taylor theorem. So whenever see there's a hint, you know, for some c in this interval, and then if you recall the Taylor theorem, there is like an arrow term at the end, right? Like this is a Taylor theorem, and the c, sorry. So this one implies in this Taylor theorem, if you want to apply, the c is actually corresponding to this value here. So that basically tells you, and also the interval here tells you where, tells you what is your alpha and beta. Alpha and beta. Because C corresponding to this X. So basically from the hint, you can figure out how to construct the correct form of Taylor theorem. Like for example, how many degree of polynomial you want to use to show this equality. And then once you do that, the rest comes pretty simple because let's see. Right, so you have shown that, and then this is equal to this, and use the triangle inequality. These two are canceled out, so you have this, right? So what you have is you have M1 is smaller equal than this, and M1 is smaller equal than this. You want to solve because your ultimate goal is what? Your ultimate goal is to show this, right? So, and so far what you have is you only have this. So you want to show, so I would suggest that you solve for H. So what is your goal? So M1 is equal to M1 squared is equal to this. And I want to show this is equal to 4M0, M2, and that will tells me what my H would be. And my H would be actually this once you do the algebra, or you can possibly do the check my work. Okay. And then the author just give us a very concrete example about how the equality will hold. I won't talk about this anymore because you can just compute the derivatives and then plug in, then you will see it is indeed 0. I don't think this one holds because during the proof we did use, I think somewhere we did use Taylor theorem. Did we? No, we did not use Taylor theorem. I will go back on this. I think it's not hold because here we're talking about absolute value. If it's vector value, then it will be vector, so it's going to be Euclidean norm. So we need to be more careful if we're doing this Euclidean norm. This may not be true because all of them are Euclidean norm. Right. Okay. Let me pause the video. Okay, so now we're on the last problem that we need to solve. It is quite long, but I feel like after all it's worth it because as the previous one, which is about the convex functions are continuous, convexity implies continuity, and we also proved that a function is convex not only if prime is smaller than increasing infinitely. F double prime is non-negative. So those are very classical calculus rules, and this one as well. So this one is about proving the Newton's method. So suppose f is twice differentiable on a and b, and we assume that f a is smaller than 0, f b is larger than 0, and f prime x is larger than delta larger than 0. And what we have is we have this for all x in a b. You might not remember all of those conditions, but that's fine. Just keep reading. So epsilon be unique point in AB at which f c is equal to 0. So we're proving the Newton's method. And for part A, choosing x1 in, so here we have A and we have B, and here we have cos C, and cos C is the 0 point. So if you have a function, it pass through cos C at point 0. And then here is x1. So we pick x1 in this way. So that is our starting point of the sequence, and we want to show. We want to interpret this geometrically. So I draw the graph, and hopefully that makes sense. So if you have functions that satisfy, so you can reread the conditions. So this satisfies all of the conditions, and the claim is that x2. The claim is that this distance is equal to this ratio. And this is because f prime of x is equal to, so f prime of x is equal to this. And then what is tangent alpha? Tangent alpha is this line divided by this line. So what I'm saying is this line divided by this line is equal to f prime of x. Therefore, this line is equal to f x1 divided by f prime f x1. So for part B, for part B showing this, I would say part B is a little bit complicated. I need some patience to. Sorry, I don't know what's wrong with my screen sharing. Let me turn it off. I think my Zoom has some issue. I will start it. I will stop here, and if needed, I will upload another video just to talk about this problem. Sorry, I just feel like my video are good, so I just go over the problem quickly to make sure everything's included in the video. So we're about talking about part B. Part B, so we want to show this is smaller, xn plus 1 is smaller than xn, and so I think for this one,